Hi everyone, I'm Elliot. I'll be presenting with Tina and Josh, and today we'll be talking about a paper called Equivalence Preserving CPS Translation via Multilanguage Semantics by Amal Ahmed and Matthias Bloom. And we'll be borrowing a lot of the visuals from Amal and Matthias's slides. So the motivation for this paper revolves around something called full abstraction. So first, abstraction and abstract data types in languages like Java and C# allow us to replace implementations with one another, and this provides some nice security features. And while these languages do have security vulnerabilities, programmers are generally aware of these vulnerabilities in the language they code in, and they can generally try to avoid them. However, when we convert from the source language, that is Java or C#, to some other target language, the issue is this may actually introduce vulnerabilities that are not present in the source language. This is a huge problem because programmers want to only reason about the source language, the language they're actually coding in, and not some other language that it ends up getting translated to. And many people have found security exploits as a result of these translations. For example, in 2006, Kennedy found that translation from C# to .NET produced holes in abstraction that led to security exploits. However, with full abstraction, we don't have to worry about this. So here's an example of how translation can lead to different behavior. So here we're translating from simply typed line calculus using CPS translation. And so we have A and B, which are two expressions that are identical in the source language. F and G are ignored, and the overall answer is 0. However, when we translate them using CPS style, we end up with A prime and B prime, and we find that they don't necessarily act the same in all contexts. For example, we have a context C at the bottom here, where if we put A prime in the whole, it ends up applying K to 1, while substituting B prime in the whole applies K to 2. So in this case, this is because we're allowing function to call its own continuation. However, CPS translation is obviously not the only issue with this kind of translation. Other cases, we can have private variables becoming publicly accessed when translating source to target. So what does full abstraction do? Fully abstract compilers are said to preserve and reflect contextual equivalence. What that means exactly is that reflection, we say, means that two non-equivalent source terms don't translate to equivalent target terms, while preservation says that two equivalent source terms translate to equivalent target terms. We see that expressed in the term below. So we have E1 in the source language, type sigma is translated to E1 in the target language, type sigma plus. E2, also in the source language of type sigma, to E2 in the target language of sigma plus. Then if E1 and E2 are equivalent in source language, then E1 and E2 in the target language should also be equivalent. So what do we mean by equivalent? Well, we have the notion of contextual equivalence. That starts with the definition of contextual approximation, which says that if we have E1 and E2, both of type sigma in the type environment gamma, if under every context and value v, then insert an expression of type sigma into the whole of the context C, terminates into Boolean, and if E1 terminates to some value v1 in the context, then there exists a v2 such that if we put E2 in the context C, it terminates v2, and v1 is equivalent to v2. And contextual equivalence just says that E1 is contextually approximate to E2, and vice versa. Intuitively, this is saying that there's no way to tell based on the behavior of these two expressions that they are different. So how can we achieve full abstraction? Well, there's three main ways we can try to achieve it. First, we could just restrict the target language so that there's no behavior allowed in the target language that isn't allowed in the source language. But the issue with this is that it won't apply to things like foreign function interfaces or multi-language frameworks like .NET. Our second option on the other side is to expand the source language, but then we're weakening the abstraction that is provided by the source language in the first place. Third option is to actually enforce this using translation. That is, we change the translation using types to enforce the property that any compiled target code has behavior that is defined in the source language. But this is difficult to prove, And the point of this paper is to introduce a novel way of proving this using something called back translation.
In order to say that our translation strategy preserves contextual equivalence, we need to be able to take two arbitrary terms in the source language that are contextually equivalent and show that their translations are also contextually equivalent. To review what contextual equivalence means, that just means that no context can distinguish between two terms that are contextually equivalent. So the strategy we would like to do here is to go by contradiction. That is, say we have two contextually equivalent terms in the source language, translate them, and then those translations are not contextually equivalent anymore. And then derive a contradiction from that. So the natural way to do that would be to say, okay, well, by definition, if the translated terms are not contextually equivalent, there has to be some context in the target language that distinguishes between those terms. And then what we would want to do is say, okay, well, somehow from that we can derive a context in the source language that is able to distinguish between the original two terms, and that breaks the assumption that they were contextually equivalent. Now, the most natural way to derive a source context would be obviously saying, okay, there's some way to translate context in the target language back to a context in the source language. However, because of the mutual incompatibility of the languages used in this paper, the authors found that difficult to do directly, or inapplicable to do directly. The two languages used in this paper were simply type lambda calculus, which you've all seen before and I won't go over again, and System F. Now, the interesting things that System F introduces compared to simply type lambda calculus is that we have typed pairs is added in as a type. We have a polymorphic answer type, and that polymorphic answer type parameterizes any appearance of functions in System F. The reason that is so that by having this polymorphic answer type, it ensures that every time a computation needs to produce an answer, it has to call its own continuation in order to produce a result of this type alpha. And that has the side effect of, it turns out, removing some undesired target terms from being well typed. And additionally, System F introduces let expressions. So in the interest of back translating terms from the target language back into the source language, the authors expand the type judgment system to include instead this translation judgment here, where we translate to these B terms in the target language. You can tell they're in the target language because they're in red. And these V terms don't represent like actual like values now. They represent computations that are waiting on their continuation to be called. And using that, they define a multi-language semantics that interoperates between the source language and the target language in order to make translating arbitrary computations now in the target language easier to back translate into the source language. Sigma division here instead of sigma plus before now just represents that we can be working with continuations instead of raw types. So to show that a context in the target language can be lifted up to the multi-language semantics is trivial, since every T context is also an ST context in the way that they've defined the multi-language semantics. If we want to take a context in the multi-language semantics that can include these computations and lift them up to the typed expressions only that is the domain of the source language, then we will have to rely on the fact that CPS is semantics preserving and semantics reflecting. And the way that the authors were able to do this was they defined a large logical relation over the multi-language semantics that, without going into details, allowed them to take these computations and bring them back down to the more simple types of the source language. However, the last step is a little more difficult, and that's because there are more ST contexts than S contexts, and Dina will take it from here to explain how they got around this.
We want to prove that if E1 is contextually equivalent to E2 in the multilanguage, then their translations V1 and V2 are also contextually equivalent in the multilanguage. This follows from the proof that CPS is semantics preserving and semantics reflecting, and they use a logical relation to prove that in the paper. So an interesting case is trying to get from E1, E2 in the source language contextually equivalent implies E1, E2 are contextually equivalent in the multilanguage. This is tricky because the multilanguage has all the behaviors of both the source and the target language. So it has a lot of things that are more expressible than what the source language can do. So there are a lot more contexts in lambda st than there are in lambda s. How they get around this is by defining these translation types and saying that if an expression has a translation type, then it's back translatable into the source language. And so we know that you can always get back to a source language term, and there's not going to be anything distinguishable even in the multilanguage context. So here is the translation type sigma plus. So booleans is just booleans, but we can see for functions, so what's going on here is a little complicated looking. When we're going from the source to the target language, we're doing a CPS translation, so we're adding continuations. And you'll notice this polymorphic alpha thing going on. So remember we had an example earlier in the presentation where we had a function ignore its continuation and call something else, and that made it distinguishable once we did CPS translation. So in order to prevent that, instead of having a universal answer type, they have this polymorphic answer type. So the function cannot call any other function instead of its own continuation. It has to in order to have the correct return type. And we can see here that they've sort of made a shorthand sigma divide for this type, which basically says it had type sigma plus before you call the continuation. So it's kind of like has return type sigma plus, and that means you can back translate into sigma. So this is the definition for the multi-language lambda st. So we can see types and values are just the types and values from the source and target language. And then terms, they do have just terms from the source and target language, but they also have these barriers. So they embed target terms into source terms and the other way around. So it allows you to have some interoperability. So it's easier to go from target to source. So we have some target expression E, and we're saying we're going to treat it as though it was a source term of type sigma. And then to go from source to target, we say we have some expression E in the source language of type sigma, and we'll just use it in E. They wanted to make it more linear, so they made it a let expression where they substitute E, blue E, for X in the target expression. Then the typing rules at the bottom. So most of the typing rules are just what you would expect, but the interesting cases are for these boundaries. But it's still pretty intuitive. So if you're trying to say that we have some target expression and we're treating it as a source expression of type sigma, and that whole expression has type sigma, then we need to know that the target expression E has translation type sigma plus. And if we're trying to say that using some source expression E of type sigma in some target expression E has type tau, then we can say, well, one, we need to prove that E has type sigma, and two, if we substitute X has type sigma plus in the type environment, then E has type tau. And then we can prove it. So here's some stuff about evaluating these boundaries. So Booleans, it's exactly what you would expect. For functions, you can see, so we have some target expression V, and we want it to be a function from sigma 1 to sigma 2. We want to treat it like that. So we can evaluate that to a lambda expression that takes an argument of type sigma 1, and then it has this boundary that is treated as though it has type sigma 2. And there's a target expression where we say let Z equal an X term in the source language that we say has type sigma 1, which is really just the argument to the function. And then it's in this expression where we pass Z, right, which is the X, to the function V, which is the original expression. And then we also give it type sigma 2 plus, which is the return type, right, for the continuation, because remember we need to pass in the alpha. And then ID is the continuation. So it'll evaluate when we pass Z in as an argument for V, and then it'll call the identity function as the continuation, and it'll return something of type sigma 2 plus, which can then be sigma 2. Then to go from source to target, again with Booleans, it's exactly what you would expect. And then for functions, it's a little more complicated. So we have some function V that has type sigma 1 to sigma 2. So we have this lambda expression that takes an X and a continuation K. And the X has translation type sigma 1 plus, and the continuation takes something of type sigma 2 plus and returns the alpha. And then we go from the X into a source, and we assume it has type sigma 1, and then we pass that to the original V, which then has type sigma 2, and then we translate that into the target to use it in evaluating passing Z into the continuation. So now we get to this interesting part where we show that we can back translate from the multi-language to the source language. So the first three rules are just saying that you can back translate terms in the source language into the source language, which is trivial. But it gets more interesting when we get to this boundary case. So we want to say that if we have some E and we are treating it like something of type sigma, and that type checks to sigma, then we can back translate to some E in the source language. So in order to do that, we need another judgment, and we say if E has type sigma plus in that judgment and can back translate to some E, then the whole expression on the bottom will back translate to that E. So now we see this other judgment, which lets us back translate not just from the source type or any part of the multi-language, but specifically from something of translation type sigma plus. So for Booleans and for if-then statements, it's exactly what you would think. And then here at the bottom, we say, well, if we have some Y that has type sigma plus and type environment gamma, then we know we can back translate to some Y in the source language. So here's the function case, which is a little more complicated, but it's not that bad really. So we say, suppose that we have some lambda function that takes a Y and a continuation K, and the Y has type sigma 1 plus, and the continuation takes an argument of sigma 2 plus and some expression E, and that whole thing type checks to sigma 1 to sigma 2 plus, which I'll explain how they can do that on the next slide. We want to show that that's back translatable to some source language lambda function. So what we need to prove that is that if we say that y does have type sigma 1 plus in the type environment, then if we can judge that substituting sigma 2 plus for alpha and the identity function for the continuation into E will give us a sigma 2 plus, and that back translates to some E, then we know we can use that E in the lambda expression, where if we give it a term of sigma 1, then we'll get some sigma 2, which is pretty straightforward. So how do they get this sigma 1 to sigma 2 plus type? So that's actually this for all alpha sigma 1 plus continuation that takes sigma 2 plus goes to alpha, returns alpha. They have this continuation shuffling theorem, which basically says you can substitute a term and the identity function into a polymorphic continuation passing function, and you can get that, sigma 1 goes to sigma 2, even though it's really like hiding under the hood this continuation thing where the continuation is the identity and we pass in the return type for the continuation, which in this case we want to be the return type of the function. So that's how that is. It's pretty intuitive, but they kind of have to do some ugly stuff to get that intuition. And so that shows that CPS is equivalence preserving for the whole thing, right? Because we can get from S to ST, we can always go back and we know it's contextually equivalent. And then it's also equivalence reflecting, which is kind of just saying the compiler is correct. So for conclusions, one of the interesting things they did in the paper was use multi-language semantics, which allowed them to break the proof up into nice, easily digestible sections. They have this idea of back translation where they have a translation type, and they show that basically if you have a term of that translation type, even if it has subterms that aren't of translation type, you can always partially evaluate to get back into something of the translation type and always go back into the source language. They have fairly elementary proofs based on syntactical logical relations, and they think that these ideas should be able to scale to larger languages, and hopefully they'll be able to prove bigger transformations fully abstract.